This will be mostly a historical talk. I think I want to give sort of an overview of Hodge theory from its origins up until essentially the work of Deligne. Some of it will be in very classical terms, and it's more to give a sense of how things developed and how they fit together than to do any particularly technical aspects. Some of the technical aspects are in the overheads, which will be on the Institute website. So if I leave some things out or skip over them quickly, I think that you'll find some of the things there. The main point of the talk will be the following, that Abel took a subject, elliptic integrals, in which there were very interesting special cases that had been worked out and completely recasted in a very general setting, and it really opened up the way for the modern theory of algebraic curves, Riemann surfaces, and so on. Similarly, I think Deligne's theory of mixed Hodge structure took a subject, classical subject of Hodge theory for a fixed, smooth, projective variety, and by introducing the concept of mixed Hodge structures, opened the subject up so that it applied to algebraic varieties, maps between them, and led to developments in a similar way to that of Abel. I begin by reconstructing Abel's theorem in its original form, which I think has always struck me as a very beautiful piece of complex function theory, and then talk about some of the developments. I'm going to particularly emphasize the work of Picard. I think it's somewhat less familiar, and also the point in Sophie's talk about considering families of varieties first appears really in Picard. So the issue about monodromy that she mentioned is there very front and center. Through Shets, Hodge, and Deligne's theory, explaining that a bit, and at the end, if I have time, I'll talk a little bit about what is more or less the current state of the subject due to Morihiko Saito, which took mixed Hodge theory and variation of Hodge structure and fused them into one object. So the presentation I'll give is subjective and impersonal. It's not meant to be a scholarly recount of history. And in particular, I'll do a few anecdotal reminiscences of things that were told to me by Shets when I was a student, Kodaira, Spencer, and even Hodge when I visited him in Cambridge. Finally, as we all know, I think classically there were issues about what by modern standards was proved and not proved. Here I sort of draw three distinctions. One is an argument that can be readily made into a modern proof, Abel's proof of Abel's theorem, for example, or Picard's version of the algebraic Dirham theorem. Then an argument that, at least to me, is convincing, but is not written out in details. I've never written it out. For example, Picard's proof of the existence of a family of rational curves parameterized by what is now the Picard variety on a surface. And finally, an argument that's incomplete, but was later done by other methods. Lefschetz's proof of the hard Lefschetz theorem and Hodge's proof of Hodge theorem, the original one. So I'll explain that. So in the beginning of the story starts with really classical complex function theory. The classical mathematicians were interested in integrals of algebraic functions. So f's a polynomial in two variables, and an algebraic function is a multi-valued function of x that satisfies this polynomial equation. And the integrals of these things were of considerable interest from geometry, arc length here on a circle, and mechanics. Particular interest were the elliptic integrals, the arc length on an ellipse. And those integrals had been the subject of a lot of study, Euler, Legendre, Gauss, and also Count Fagnano. And it was really he who discovered what is called the addition theorem for, well, we now call it an addition theorem for elliptic functions. He had a formula for doubling the arc length on an ellipse, similar to the way that you double the arc length on a circle by the formulas for sine of 2 theta and cosine of 2 theta. Also much studied, and in a way mathematically simpler, is the arc length on the limnoscate. Here I've just drawn the picture, and this is a particularly nice integral to play with. All right? It's a simple integral. You have 4 branch points, the 4 roots of unity. It's a Riemann surface of genus 1. The integral was understood to be a function of the upper limit of integration. That's the way these people thought about it. And really what they thought of is you choose some path of integration. This is multi-valued, but choose a path from here to the upper limit of integration. And they were interested in what sort of function do you get. And even though you're integrating an algebraic function, the functions that you get are, of course, transcendental. And what sort of transcendental objects are these? So a different choice of path changes this thing by a period. So if, whoops, I've got to get used to this machine. If you go around this way, you'll get some integral around a closed path. That's called a period. And that was really the beginning of Hodge theory. The degree of multi-valuedness of these indefinite integrals. I should just mention in passing that when you take your polynomial and your rational function to have coefficients in a number field, then the transcendental character of this is a subject of great interest, works of Siegel and also Enrico here over the years. So these indefinite integrals have both geometric and arithmetic interest. When the degree of the polynomial is, it should be 2, not 1. The degree is 1, they are elementary functions. And when the degree is 2, they're still also elementary functions, these integrals, simply because a conic, that's a degree 2 polynomial locus, is really parameterized rationally. So you change variables in the integral, and you get essentially the integral of a rational function on the Riemann sphere. But once you get to degree 3 or more, the story changes. These were things that were of a different and much deeper character. There were a number of specific results, but then Abel recast the subject, introducing 2 concepts, abelian sums and for inversion. For abelian sums, what he did was consider your fixed curve. Here I've taken the Weierstrass cubic, and a variable family of curves depending rationally on a parameter. Here I just took a family of lines. And you look at the intersection. So the line meets the cubic in 3 points. And instead of looking at these individual integrals, he considered the sum of the integrals to all those variable points of intersection as a function of the parameter t. And his theorem is that this is an elementary function. That is, the derivative is a rational function. Okay? So that was Abel's theorem in its original form. The individual integrals may be very highly transcendental, complicated objects, but this abelian sum is something understandable. It's a very general result. The only implicit assumption is that this polynomial has no multiple factors. The proof goes through in that generality. In fact, in modern terms, the proof was this, that you look at what's called the incidence correspondence of points on the curve and points where the lines meet the curve. So it's these 2 equations so that's the I. So it's an algebraic variety that's called the incidence variety. And it projects onto the curve, and it projects onto the t line. And what you're doing is taking a differential here, pulling it back, and pushing it down, taking the so-called trace. The trace means that you average over the inverse image of a point. So you, instead of averaging a function, you average a differential. And you get a rational one form on the projective line. That's now an easy result. If you do it by local considerations, it's single valued just by construction. So you need to show it's meromorphic to show something is meromorphic means it doesn't have an essential singularity, and that's just by local considerations. Nothing in the integral can make things grow exponentially. When degree of f is 3 or more, a new phenomenon occurs in that you get, in that case, when the differential is of this form, and I'll explain why things were taken of this form, this abelian sum is constant. The point is that with this degree restriction, the trace is a holomorphic differential on the Riemann sphere. There's no holomorphic differentials on the Riemann sphere. Okay? This particular form is because what people considered classically was the differential on the curve to be the residue of a differential in the plane with a first order pole on the curve. So that was the first point of Abel, that you look at abelian sums rather than the individual integrals. The second point was to define implicitly of the x and y as functions of the value of the integral. So you invert the integral. And Abel's theorem then translates into an addition theorem for these functions, which are the upper limits. It's a functional equation that they satisfy. So for example, for the cubic I had a minute ago, if you choose your reference point properly, this is simply the functional equation that you get. Okay? And what that gives then for the x-coordinate and the y-coordinate at the sum u1 plus u2 with a minus sign is that those are rational functions of the coordinates at u1 and u2. That's the addition theorem for the Weierstrass p function. So I think Abel really viewed what he did as these mysterious integrals that if you invert them, that the upper limits of integration do have addition theorems. They satisfy functional equations. That was really, I think, his concept. An important point here is that the curve can be singular, and so I'll use a little modern terminology here. In hindsight, what Abel was using is what we now call, due to Pierre, the mixed Hodge structure on the curve to describe the generalized Jacobian. And here I've just written a few words to explain what that is. The regular differentials for a smooth curve and a possibly singular curve give you what is called the F1, the first level of filtration in the mixed Hodge structure of the curve. Okay. So Abel's theorem opened the gateway to the modern theory of Hodge structures. Jacobi, who formulated the Jacobian variety by taking, for a smooth curve, the dual space of the differentials modulo periods, and proved the inversion theorem, which I'm not going to recall here. Well, I guess I will recall it actually. In more detail, when you have a smooth curve, it's a complex submanifold of the projective plane, so it's a compact Riemann surface. These are the holomorphic differentials, and the periods are just the integrals around elements in the first homology. That's the beginning of Hodge theory. Choosing a base point, the abelian sums are just expressions of this form. You integrate from your base point to variable upper points. So this gives you a map from configurations of points onto the curve into a vector space factored by a discrete subgroup, a lattice, the lattice of periods. And here I've just drawn the picture. If you go a different way from P0 to P1, you change this integral by a period. So this object, this quotient of the vector space, dual to the space of differentials, modulo what you get by periods, it's a complex torus, and the geometry of this map, configurations of points on the curve into this Jacobian variety, that's really the key to unlocking the geometry of algebraic curves from this point of view. Riemann came after Jacobi. He showed that, in fact, the dimension of the space of holomorphic differentials is 1/2 the first Betti number, or in modern terms, the first cohomology decomposes as a Hodge structure of weight 1. The direct sum of this and its conjugate are usually written this way. Okay? So it's Riemann who, if you like, put a Hodge structure of weight 1 on the first cohomology of a compact Riemann surface. I think I'll skip that. I'll come back to it. Yeah, the next thing I want to talk about is Picard. But before discussing him, I want to say just a little bit about Lefschetz, because it's very interesting historically, that he was born in Moscow and moved to France, and there he was a student of engineering. He loved mathematics, but he thought he couldn't get a job in the French academic system at that time because he was not French, so he studied engineering. And he came to the United States and took a job with Westinghouse in St. Louis. And he was working in a boiler room when the thing blew up, and he lost both of his hands. So the rest of his life, he went back into mathematics, and with the help of his wife, he was able to write mathematics, and he became a mathematician, if you like, at least in part because of his experience with the accident. He went to school at Worcester Poly in Mass, small school. They had only 3 faculty, one of whom was a student that came out of the classical algebraic geometric school of studying plane curves. Lefschetz's thesis problem was how many double points and cusps can an irreducible plane curve have? Old problem in algebraic curves. He took a job at the University of Kansas, and he was there for 10 years. That's where he did his work on the topology of algebraic varieties, which I'll say a little bit more about, but I think is fairly well known. It's also where he proved the fixed point theorem that you heard about earlier today. Interestingly, he was not allowed to teach complex variable at the University of Kansas because they said he didn't know the subject well enough, didn't trust him with it. Coming to Picard, he studied algebraic surfaces, which for him were given very concretely by a polynomial equation in C3, or really projective P3. And this would be a surface with ordinary singularities. The way to think of it is you have a smooth surface in high-dimensional space and generically projected into P3. It becomes a surface of codimension 1, but it'll have singularities that arise from the projection, but they were well understood what those singularities were. So in modern framework, he was going to study this surface by fibering it by these curves. You hold the y-coordinate equal constant, you get an algebraic curve in the xz plane. So that again ties in with what you heard in Sophie's talk earlier. Look at a family. In modern framework, you take what's called now a Lefschetz pencil, this family of curves. You blow up the base points where they intersect at infinity, and you get a smooth surface fibering over P1. The picture Picard drew was to picture this surface. You take the parameter space, the y-plane, you fix a point corresponding to a smooth curve, and you look at the points where you get singular curves. So you think of a surface in 3 space and look at a parallel family of planes. They will occasionally become tangent. Those are singular fibers. So there are a finite number of them. He drew them in the plane and traced out paths from the smooth reference curve to the singular ones. The rest of the plane is simply connected. And so what happens is the whole algebraic surface retracts onto the part that lies over the skeleton here, this family of curves traveling along these paths. Okay. The singularities were well understood. Locally, what the singularity you would get, and think now of the curve as a Riemann surface. This is a little piece of the Riemann surface. The equation looks like that. Or if you think classically, you would say U is this algebraic function, and it has branch points at square root of t and minus square root of t, with the property when you analytically continue across the slit, it changes value. That was the way they pictured this thing. Topologically, it looks like this. And locally, the topology then is that this cycle around the middle, it's called a vanishing cycle, goes to the point. And this cycle that runs from the top to the bottom is the one that's interesting, as I'll explain now. So the surface topologically was pictured something like this, that your central fiber goes out on these, cuts to various singular fibers, and the whole surface retracts onto this real three-dimensional object. So a key to understanding this thing is the monodromy. How does the fundamental group act on the homology? You take out the singular fibers, you're left with a fiber bundle in the sense of topology. So the fundamental group of the base acts on the homology of the fiber. What is that action? That was the key. First step is to find the local action around the singular curve. And here again, we come back to Shets. Picard drew the following picture, that if you go back 2 overheads and look at this curve here, or if you like the straight line that comes down the side of the cylinder, and you go around the singular point, you end up with this. You can sort of see that when you interchange the branch points, you drag the thing around. And Picard said that that in homology is the same as this. Shets said he spent hours staring at this picture. What does this mean? Actually, it's interesting that Picard arrived at this analytically. He was thinking really of the integral along this path that goes there. And analytically, he wrote down a differential equation that satisfied and showed that analytically it was this function, it was given by this way. Okay? So that told you how the path of integration changed from the differential equation satisfied by the integral. So this gives the local monodromy, if you like. This curve, which requires a node, pinch is here. The cycle that goes around the handle comes back to itself because you can pull it away from the singularity. The cycle that goes through the singularity goes to itself plus the cycle around. It's the Picard-Shets formula. So Picard divided the cycles on this algebraic surface into 2 kinds, those that were invariant under monodromy and those that vanished. That is, the ones that when you took the inclusion map of the first homology of the curve into the surface, they became boundaries. Those were the vanishing cycles. The global monodromy, that's a story that we'll come to. So the local monodromy was well understood. The global one, we'll come to that. On differentials, Picard studied differential 1 forms. They look like this, or 2 forms that look like this. And for the holomorphic 1 forms, the things that were holomorphic on the fibers, he divided them into 2 groups. And in modern language, what he's doing is taking this surface that you get by blowing up the base points that fibers over the projective line, taking the direct image of the relative canonical bundle, that's the differentials along the fiber, and Picard showed that it was a direct sum of it has a certain trivial part and a certain part that was a direct sum of these standard line bundles on P1. So there was a part of the holomorphic differentials that were sections of a trivial bundle, so they're sort of constant. Those are the holomorphic 1 forms on the surface restricted to the curve. Okay, Picard proved that. The proof is correct. And then you have these over here, which we'll come to in a minute. Shets, by the way, the critical thing in Shets' 1-1 theorem, his famous 1-1 theorem, was to identify these here, where these ki are at least 2, with the holomorphic 2 forms on the surface by the map. On the topological side, Picard gave a correct proof that all of the first homology on the surface lives on the curve, on the curve. The map is onto, and that the second relative cohomology is generated by those cones that you get by taking this cycle that vanishes when you go to a critical point. These are correct. They just follow from his description of how you retract that the whole algebraic surface onto the skeleton. But here things got a little murky because he asserted, well, the first homology is the direct sum of the vanishing and the invariant cycles. And moreover, the dimension of the invariant part is twice the dimension of the space of invariant one forms. Well, we now know that this statement here is true, but I think the proof in Picard, it's not clear whether it can be made complete in that special case because there was the theorem of complete reducibility of the abelian varieties that Poincaré had. So you get something. Whether you get enough or not, I'm not sure. But this direct sum decomposition, if you like, of the global monodromy, in this case just the invariant and the vanishing, but in general the direct sum, that comes out of mixed Hodge theory of Deligne. I think I will skip this because I'm going to run short of time. I would just mention that one of the interests of the classical mathematicians was to classify differentials on an algebraic variety. On a Riemann surface, they are classified into three kinds. The so-called first kind, these are the holomorphic differentials. The second kind, these are the ones without residues. So if you like, they give cohomology classes on the whole algebraic curve. And the rest were called differentials of the third kind. Picard wanted to do that for algebraic surfaces. For one forms, he did it correctly. It was more or less the same as for curves. But for two forms, well, the first thing he did when he came to two forms was he gave a correct proof that the second cohomology with complex coefficients on the desingularized surface was given by what we now call it's the algebraic Dirham theorem. If you look in Picard, he gives this argument correctly, I believe. Yeah. Okay. He had control over the hyperplane at infinity. It was smooth, so he knew that. If he had to get into the singularities, then it was another story. But in this case, he knew it. But there was a new phenomenon here, that for two forms, he found that there are two forms that are holomorphic in the affine part, in the finite part, and the C2 sitting in, or C3, the part sitting in C3, sitting in the projective 3 space, but they became exact. They're exact, but the pole of the right-hand side is bigger than the pole on the left-hand side. So it's something, it cannot happen for one form. If you have a differential form just in the complex plane that's exact, so omega is d of f, the poles of f cannot disappear when you take d of it. But poles could disappear here. And Picard identified how this could happen and showed, in fact, that the way it could happen, the dimension of the set of two forms whose poles, when they became exact, the poles went up, was equal to what's called the Picard number, or the rank of their own Severi group. So this was the first appearance of algebraic cycles giving homology classes on, in this case, an algebraic surface. And this argument here, I believe, is correct. It also focused attention on homology classes carried by algebraic curves or algebraic one cycles, and that, of course, is part of the modern Hodge conjecture. I would say, though, that all of the classical results of this kind, the classification of differentials of the first, second, and third kind, and then Shets tried to do it for higher dimensional varieties, but there it gets a little squirrely. These are just all explained beautifully by mixed Hodge theory. You know, you just unwind what mixed Hodge theory tells you, and out comes everything that the classical folks knew. As for Shets, he wrote, I think, very nicely that what he did was put the harpoon of topology into the whale of algebraic geometry. And I will not recall his results on the topology of algebraic varieties. I think those are fairly well known. I do want to comment a little bit on the so-called hard-Lefschetz theorem. So if you go back to the picture Picard had, if you have this family of algebraic curves, family of compact Riemann surfaces, you take out the singular fibers, and suppose you have a homology class in degree 1 that's invariant under monodromy. You say, well, let's let that just trace out something of dimension 3. It's invariant when you go around the singular point, and it's invariant around infinity. That's taken care of. So it traces out a 3 cycle. So the locus of a 1 cycle that's invariant is a 3 cycle. And generally call this, whose intersection with the central fiber was the thing you started with. That defines a class in the third homology. Okay. This is correct. And the hard Lefschetz, though, is the statement that intersecting the third homology, well, first, it defines a cycle here, and every cycle here comes in this way. It comes by the locus of an invariant cycle. Okay, that is correct. What Lefschetz claimed was that the intersection from the third homology to the first homology, you just take a 3 cycle, put it in general position, intersect it with this hyperplane section, this curve, that's injective, which is the same as saying that the vanishing cycles intersect the invariant cycles are 0. And this argument is incomplete. And if I remember, Pierre, we once talked in Bure, and you asked me, was the Lefschetz argument complete? Because you said if it's complete, then I think the Weil conjectures will follow. I believe, or should follow.
The reason is that Lefschetz was not using Raphael and for those and it froze.
So, and anyway, you'd be a long way along. But and the reason is that you can construct the topological picture of a surface, algebraic surface, fibered by curves with just ordinary double points, the whole picture in which this statement is false. It's not a purely topological statement. It runs much deeper. This is just an anecdote about Lefschetz, but, well, I'll just say, I mean, you can read it here. So even though Lefschetz, I remember him very well being of this sort, he would say, we're not babies, are we? I mean, this is clear. But in fact, it wasn't clear. He had incredible intuition, so he knew what was correct, but what was true, but he didn't know. I mean, it was said about Lefschetz that he never stated a false theorem nor gave a correct proof. So anyway, coming to Hodge's book, the purpose of his book was to prove the theorems that Lefschetz had proved about the topology of algebraic varieties using differential forms. Dirham's theorem had just been proved, and he wanted, using differential forms, to prove the Lefschetz theorems. He had as a model the book by Hermann Weyl on Riemann surfaces, which to me was the first really modern, at least differential geometry or manifold book. And it's the first definition of a manifold, Dirham theorem for the first cohomology of a surface. All of these things appear in this wonderful book. He proved these statements here. Their proofs are modern. And he used harmonic theory. He showed that the first cohomology was represented, each cohomology class was represented uniquely by a harmonic form, one that minimizes this integral here, where the star operator comes off the conformal structure on the Riemann surface. So Hodge wanted to do this in general. You needed a Riemannian metric to define the star operator, but he introduced that, and he introduced the notions of harmonic forms. His work fell into 2 parts to show that the Dirham cohomology was isomorphic to the space of harmonic forms, things that minimize the L2 norm in a cohomology class. and then the very special structure of the harmonic forms when you have a Kähler manifold. I'm going to talk about B in just a minute, but there's a nice little story here about A, that the importance of Hodge's work was recognized, of course, in particular by Hermann Weyl, who was here at the Institute, and he was giving a seminar, and it became, I think, reasonably clear in the course of that seminar, when you look at the notes that come out of it, that Hodge's theorem was certainly a correct theorem, but the proof was incomplete. And so what Hermann Weyl did in the seminar, in order to give the complete proof, was to devise the famous Weyl lemma, that if you have a function that's in L2, and it's a weak solution of Laplace's equation, or more generally a second-order elliptic equation, then it's smooth. So the regularity of linear elliptic equations came out of, historically came out of Hermann Weyl fixing up the proof, completing the proof of Hodge's theorem on harmonic forms. Anyway, the second part was done by calculations, and the calculations in Hodge's book are nothing short of a tour de force. I mean, there are indices all over the place. I don't mind the indices up to a point, but this was really something else. And, you know, one has sort of cleaned things up a bit now. The two main points are to show that the Laplacian commutes with a projection onto PQ forms, and to show that the Kähler form commutes with the Laplacian. So the Laplacian maps forms to forms. The Kähler form, you wedge a form with it, and that maps a form to a form of degree 2 higher. And if you write down what the Laplacian is on a product, it's a mess. You get two terms that you know are there, and then you get a big mess. And there's no reason in the world that the big mess should go out when you plug in the Kähler form here. Hodge told me, when I asked him about this, I said, how in the world did you think of this? He said it was the only way that I could prove Lefschetz's theorems. You know, it had to be true if the proof of Lefschetz's theorems were going to come out of this. So, you know, my guess is that if you take a general positive 1-1 form and you assume that the big mess goes away, that's equivalent to its being closed, being a Kähler metric. So that the big mess being 0 is sort of equivalent to the Kähler condition. I mean, I've never checked that, but I think that's likely to be true. In any case, one then gets the Kähler package that the cohomology decomposes according to the way a differential form on a complex manifold decomposes into PQ type. You have the Lefschetz operator, which maps you from cohomology above the middle dimension isomorphically to cohomology just below the middle dimension. That's that intersection of H3 to H1 that I mentioned in Picard that was not proved. And if you look at the so-called primitive cohomology, that's the kernel of the next higher power of L, then the whole cohomology decomposes into its primitive parts. And on the primitive parts, you get what's called a polarized Hodge structure. So that's not only a PQ decomposition on cohomology, but they're bilinear forms with positivity conditions on them. I would, for later, I'm going to skip that. For later purposes, the Hodge decomposition is equivalent to giving the Hodge filtration, where the upper index means having at most that many DZs in the differential that you're looking at. So giving a Hodge filtration means that you have this, and this is the relation between it. From the Hodge decomposition, from the Hodge filtration, you get the Hodge decomposition and the other way. And then I would just note that the existence of the polarization, that's a critical fact. I think a general Hodge structure is of modest, if any, interest. When the polarization comes in, then you begin to get some geometry. And I think I will skip this, the Kadara-Spencer part. So what I was doing there was just talking about some of the uses of Hodge's work by Kadara and Spencer in the 50s where they completed some of the classical things like the existence of a family of rational curves parameterized by what's called the Picard variety. The Picard variety on a surface, the Picard variety is the generalization of the Jacobian variety of a curve. And this was in existence there. This shows that if you have an algebraic curve on an algebraic surface, that you can deform it rationally with a certain number of parameters. Coming to the 60s, there were a few fragments of Hodge theory for singular varieties. Everything I said from Hodge was for a smooth, compact Kähler manifold, in particular, if it's algebraic, a smooth projective variety. Hodge theory, there were generalized Jacobians of algebraic curves, which in a way were almost a rediscovery of what Abel was doing, but put in modern terms by Rosenlicht and others. And there was also the Hodge theory for the singular fibers in a Lefschetz pencil. That is, if you took the Picard picture where you have very controlled singularities, just ordinary double points, then you knew what happened to the Hodge theory when the thing became singular. You could just work that out by hand. Two things happened. One was Hironaka's resolution of singularities, and the other was Deligne's mixed Hodge theory. It's interesting to note that in their paper where they were trying to bring some order to the classical literature on differentials of the first, second, and third kind, that was where the appearance of what's called the log complex by Atiyah and Hodge appeared. Okay, so that if you have resolution of singularities, something singular that's maybe very complicated can be blown up to look like just the union of linear spaces meeting transversely in Euclidean space, then the differentials with singularities along such a thing are just of this kind over here. Whoops, where's the pointer? That, logarithmic differentials. Okay. In fact, Grothendieck, when he wrote his paper on the algebraic Dirham theorem, said, well, Atiyah and Hodge knew the proof but not the theorem. Anyway, coming to the story of mixed Hodge theory, a mixed Hodge structure is given by the data of a Q vector space and increasing filtration over the rationals and a decreasing filtration over the complexes. And it should satisfy this condition. The way to think of this condition is that you have this increasing filtration. So you have a vector space with increasing family of subspaces. You can look on the associated gradeds. And there, this filtration should induce a Hodge structure of the appropriate weight. Okay? So this is the definition of a mixed Hodge structure. So it's the successive extensions of a special type of Hodge structures. They admit the usual operations of linear algebra. You can talk about morphisms between them, tensor products, direct sums, and so on. The most, to me, one of the essential linear algebra properties is what's called strictness, that if you have a linear map between two vector spaces with mixed Hodge structures that preserve the weight filtration, preserve the Hodge filtration, then anything that ends up in filtration level P comes from something of filtration level P. The maps are strict in this sense. It's from that that you get that they form an isabelian category, mixed Hodge structures, and so on. Deligne's theorem then is for a complex algebraic variety. The cohomology with Q coefficients has a functorial mixed Hodge structure. For a complete variety, a compact one, the weight filtration goes from 0 up to the degree of the cohomology. For a smooth and open, it begins at the degree and goes up to twice that. So in general, it goes from 0 to twice the dimension. Given the presence of the presentation of an algebraic variety in terms of smooth ones, where by smooth I include normal crossings, so it's smooth things intersecting transversely, it's sort of feasible that you can write any cohomology class and you can resolve it into cohomology classes that are supported on smooth, complete objects. Okay. What's not clear is that writing it, if you like resolving it in this way, gives you anything useful. And secondly, is it well defined? So to say that it gives it something useful means, well, technically what Deligne proved is that a spectral sequence degenerates so that when you write, you resolve the cohomology of this variety in terms of the cohomology of smooth, complete varieties, that what you get doesn't get you too far removed from a classical Hodge structure. It's a mixed Hodge structure. And secondly, that the thing is independent of the resolution of singularities. Okay? Not at all clear on the face of it that this should be the case. So I think it's safe to say that this result, together with the next, what I'll next mention, really opened up the study of the cohomology of algebraic varieties in a similar way to what Abel's theorem did to algebraic integrals in one variable. I think I'll skip that. A special type of Hodge structure arises when you have a nilpotent endomorphism, and then there's a unique, what's called monodromy weight filtration coming from that nilpotent endomorphism that satisfies these two properties, that, that they drop the weight by 2, and they're an isomorphism about the middle. So it smells like the Shets theorem. The way to think of the weight filtration is just the general theorem of Jacobson-Morozov that any nilpotent transformation can be completed to an SL2, and where this is the matrix 0, 0, 0, 1, one in the lower left-hand corner. So if you think of the representation theory of SL2, then this just decomposes a module of an SL2 module into its irreducible pieces. Okay. So the special type of mixed Hodge structure is called a limiting mixed Hodge structure, is one where the weight filtration comes from a nilpotent endomorphism, and it shifts the Hodge filtration only by 1. The way that these things come about is, again, going back to Sophie's talk, if you have a family of algebraic varieties over the disk now, which are smooth outside the origin. Over the origin, you can fill it in with, say, a normal crossing variety, something that's a union of smooth things meeting transversely. You want to know what happens to the Hodge theory as you go into the origin. And this is subtle because what you're looking at is the Hodge filtration on the cohomology of the fiber over T, but that is not a constant vector space. So what do you even mean by analyzing the Hodge structure as you go into the singular fiber? Where this n comes from, by the way, is that the monodromy around a singular fiber is quasi-unipotent, satisfies this condition, and replacing it. So the eigenvalues are roots of unity, which is again reminiscent of the previous talk. And just by taking a branch covering of the disk, you can assume that the monodromy is unipotent, so it has a logarithm. That's the n. So what Schmidt proved was this result here, that if you untwist the Hodge filtration, so you essentially identify all the cohomology of the smooth fibers with a fixed vector space, then you get a well-defined limit at the origin of the Hodge filtrations. Okay, Schmidt proved it for any variation of Hodge structure. Steenbrink did it in the geometric case, and a several variable version was done by Catani, Kaplan, Schmidt with significant input, I think, from Deligne again. And did I get to, I didn't get to the punchline, which is, I think one of the overheads was missing here. Yeah, one of the slides is missing, so I'll have to fill it in verbally. So you have this what's called limiting mixed Hodge structure, the weight filtration coming off the log of monodromy, the limit of the Hodge filtrations as described here, and that gives you a mixed Hodge structure. And on the other hand, you have this family of smooth varieties over the punctured disk, and the way that the Hodge structure on the smooth varieties behaves relative to the Hodge structure on the singular variety is captured by the limiting mixed Hodge structure. Okay, it was conjectured by Deligne, proved by Schmidt. So if you want to know in a family of varieties acquiring singularities, what happens to the Hodge structure, it's encoded in the limiting mixed Hodge structure. Okay. Sorry, it's on my, I have a printout of it, but it's not on this one. So coming back to general mixed Hodge theory, one of the first applications of Deligne's theorem was where you have a global, in this case, a global parameter space, as in Sophie's talk, of smooth projective varieties. And you have the monodromy representation, how the fundamental group acts on cohomology. The image is called the monodromy group, and it preserves the polarizing form. It's important here that you have the polarizing form as part of your picture. So the local monodromies around the singular things that you've taken out, those are, if you like, in Jordan form, upper triangular things. Ones on the diagonal, stuff above the diagonal. Globally, as a consequence of Deligne's result, the monodromy is semi-simple. So the old statement Picard made that the invariant cycles intersect the vanishing cycles as zero is in fact a very special case of this very general result, the simplicity of global, semi-simplicity of global monodromy. I think I'll say just a little bit because of time about the Saito stuff. And I think I'll just refer to the file that's going to be on the Institute website for this latter discussion. It talks a little bit about some of the existence questions for algebraic cycles. In the early 80s, Balanson, Bernstein, Deligne, and Gauber developed a Hodge theory of maps. This began way back in the early days. There was a theorem proved by Blanchard where you have a family of compact Kähler manifolds over a smooth algebraic curve. Then the Leray spectral sequence degenerates at E2. And Deligne proved this in general. So when you have only smooth fibers, you get a very simple situation where the Leray spectral sequence degenerates. Okay. What happens, that's a one-dimensional base. What happens though, well, even when you have a one-dimensional base in singular fibers, you can still figure out what happens. It's pretty simple. Okay. Once the dimension of the base is 2 or more, the issue is much more subtle. And here again, like in the case of Hermann Weyl and the regularity of linear elliptic equations, the Institute, I think, played a role here, people at the Institute, in that what was needed to talk about the Hodge theory of maps was the intersection cohomology of a complete singular variety created by Mark Goreski and Bob McPherson here. That's what enters into the description in the Hodge theory of maps. If you want to say what happens when you have a map between arbitrary varieties, or say smooth varieties, but arbitrary dimension-based, arbitrary singularities, what can you say about how the cohomology behaves in that situation? That's the Hodge theory of maps. Saito stated objective. So this was done by characteristic P methods, Frobenius, which we heard about earlier, acting on cohomology. I think that's correct. It needed Frobenius to prove the original version. Saito wanted to prove this in a purely Hodge theoretic setting for Kähler manifolds, say. So the building blocks of his theory are variations of Hodge structure and admissible variations of mixed Hodge structure, how the Hodge structure behaves in a family even when they're singular fibers, and D-modules and perverse sheaves. The perverse sheaves being the sheaf theoretic version of intersection homology of Goretzky and McPherson. Very informally, Hodge modules, this is the way I think about it, are the smallest category of objects over smooth varieties that contains generically on the complemented divisor a polarizable variation of Hodge structure. Or mixed Hodge modules are the same with admissible variations of mixed Hodge structure. So suppose you start out and you know first the cohomology of a smooth variety. Then you know also how the cohomology of a family of smooth varieties varies in a family. And then you know finally what happens to the cohomology of a family of smooth varieties in a one-parameter family when you acquire singularities. Okay. So putting all those together, you want to construct a category which reduces to that in all the special cases. And in particular, you want to know that if you start with an object in this category and a map, that you can push it down. What happens when you push forward, say, an admissible variation of mixed Hodge structure? Okay. That's what Saito, it's fairly complicated in the technical details, but that's what he worked out. There's some applications of what he did. I'm going to skip over those. Those, as I say, are again on the website. A concluding application that I want to do, what I do want to mention, is something that's a current project, actually, or a current conjecture, which is something far removed from algebraic geometry in the sense that I've been describing it, periods of integrals on algebraic varieties and their generalization. What Schmidt and Valonen were interested in is the following, that if you have a real semi-simple Lie group with Lie algebra, G maximal compact subgroup, then there's certain what are called admissible GK modules, Harish-Chandra modules. So those are things that arise from representation theory of real semi-simple Lie groups by algebraizing them in a certain way. Okay? They're easier to study than unitary representations directly. So these are the Harish-Chandra modules. These Harish-Chandra modules, the irreducible ones, were classified a long time ago by Langlands, reclassified by Bailenson and Bernstein. The important issue, though, so these are general Harish-Chandra modules, nothing having to do with a unitary representation of a real semi-simple Lie group, which is the ultimate object of interest. So the question is, among the Harish-Chandra modules that you know, which ones are unitary? Recently, there was an algorithm developed by Vogel, which in some sense gives an answer to this question, but it's not, in a way, a satisfactory answer in that it's sort of like proving something exists by saying it's the unique, irreducible subquotient of something else somewhere. You don't know what it looks like. You can't hold it in your hand. Schmidt and Valonen wanted to be able to say directly from the structure of the Harish-Chandra module when it's unitarizable. And what they have found is that there's a certain Hermitian form, which I won't describe, and the question of deciding when something is unitary can be boiled down to knowing something about the signature of this Hermitian form. What Schmidt and Valonen do is interpret the form as a polarization on a mixed Hodge module. Okay? And conjecture that this polarization satisfies the second, if you like, the analog of the second Hodge-Riemann bilinear relations. Okay? If that's true, then you have finally the description of the unitary, irreducible, unitarizable Harish-Chandra modules done using the Saito theory, the mixed Hodge module stuff. So, as I said, this has nothing to do with Hodge theory and the sort of setting that I've always thought about it, family of varieties with Hodge structures. It comes completely from representation theory and the Saito theory. And so it just shows that, if you like, the formalism of Hodge theory, which really, I think, in my mind, originated with mixed Hodge theory, has much wider applicability than just to our good old, my good old algebraic varieties. Thank you.